Okay, I recently wrote a blog post, and it had some it was called Tradeoffs in Engineering, but it also highlighted a bit about a systems design that I got to work on, and I didn't really write about too much about how it was architected, but I got some general interest in, well, how was it really architected? How does it work? This is the blog post in question, Trade-offs in Engineering, and it really was just a blog post just talking about, well, we have current situation of I have these current resources, these are what I'm restricted to, let's try and build something, but, well, I only have but so many hands. Anyhow, that's more or less the gist of it. The systems design, I didn't really write through too much of it. There's only this little bit of a architectural diagram, which really doesn't go into too much detail. But I figured I should try and do a little systems design. So I have draw.io open. It's a blank canvas. So that's what I was hoping to get through today. Alright, so let's draw the initial architecture of the system first. We'll go with some random squares. We could make this pretty later. But we had general API layer. Let's copy and paste this. We had let's make this one front end. This is React. All it did was front end talks to our API. I think I can get some fun shapes here. Sort of. That's the MongoDB icon. Oh, okay. We'll use the actual icon. There we go. And we had our API talking to MongoDB. We had S3. Yep. To store things too. We'll go with that. Well, yeah, that was pretty much it. So this is what we end up calling the initial architecture. So this is our initial architecture. It's just very plain and simple. We had our application, our front-end application that had connectivity to our API pods. These were all in Kubernetes, if that makes any more sense to have had that written out. Oh, it says API, look at that. But these are Kubernetes pods. Also, front end was talking to Kubernetes, but Kubernetes is the important part for why, the reasons of why for API. So let's specifically have Kubernetes here first. But we have our front end talking to our API, which was able to fetch data from MongoDB. Was able to fetch and write data to both, to S3 as well. So typical architecture here, nothing too fancy. The problem we had that was scoped out in this document somewhere is that, well, yeah, probably under the problem bits, was that we had more enterprise level customers where enterprise comes with larger sites, so it was a scaling issue. Enterprise customers come with larger sites, and our site restores started failing this this process. So if we, let's see if, can we zoom in here? Ah, okay. There's a synchronous request, rather. So, meaning that the front end needed to wait until the API completed. For this entire process, It was baked into the API itself, but we'll represent that with a new rectangle. This is the giant restore process. And I mean giant meaning like it was literally fairly large. But within our API, we had this cool. All right, so within our API layer, we had a giant restore process, and all it did was, on the front end, we would have an API request to restore a site, and it would trigger this, and if it completed, it was successful. If it did not, well, there was an issue. So most of the issues came with timeouts from Express. So this is a Express API, timing out at 60 seconds for the front end. And oftentimes, more than not, the way to fix this for our customers was to add, customers would call in or write in with a support ticket, and with Kubernetes you are allowed to have these sidecarts. So API sidecar pod. So this is not a new API itself, but rather it's just a separate Kubernetes pod that is not completely tied to this API. So think of it as just an additional Kubernetes pod, but no production traffic is serving to it. It's just spun up for a customer service representative. This means that the customer service representative can run a command to basically handle the site restore, to fetch the MongoDB collections, fetch the assets from S3, and then that bypasses the 60-second timeout. So this is the initial architecture, and how did we end up improving it is a nice question. What we wanted to do was we had this synchronous request. We basically wanted to make it asynchronous, like completely asynchronous. And how did we end up doing that? Asynchronous just kind of hints at, hey, we want some SQS here, so we added new infrastructure of SQS. They still talk to Mongo and S3 regardless. We still have a giant restore process. When there was a request to the API, it would end up going to SQS itself. So what ended up happening was we also had not a sidecar, but a worker for the job. All right, we moved this giant process to be completely run within the worker. So let's move this down over here, actually. This is the giant restore process. And instead of it running in the API, it's running in a asynchronous worker job now at this point. There is some logic that we did add, but that's basically what happened here. So this is now milestone 1 of from glossing over some minor details, but front end more or less stayed the same. We had to make some UI updates to support an asynchronous flow. So there were like some toast notifications in the front end that we added saying that, hey, your job is being enqueued. There was some nice language that we added to it. Your site is being enqueued for restore. Here's another toast of your site restore is complete. And you got that in a nice notification bell in your dashboard. To go through the flow, a customer ends up triggering a site restore. This is now an asynchronous request, so once that's triggered, they get that toast notification on the front end. In the API itself, that is now a request to just enqueue into SQS. It's enqueued within SQS. Once the job is picked up, the worker picks that up and runs this giant restore process completely or not. So this is milestone 1. Very simple architecture, not too crazy. So the problems that I was alluding to in the beginning was we got past this 60-second timeout here. That was the problem, no longer a problem. We started seeing issues with well, these are now long-running processes in this worker, and as part of the entire application, Kubernetes pods would often restart themselves if there was a deploy, or if there was well, anything wrong with the pod that could typically just cause pods to restart. This caused some issues with our giant restore process, but luckily we saw that within the observability metrics that we added, that within this giant restore process, there was actually tinier processes that could be broken down into, well, smaller ones. So we had this giant process, and this is, let's say, function 1, this would end up being function 2, etc. So you kind of get the point here. There is, we'll call this n at this point. Within this giant restore process, it was built in that there was like multiple helper functions, and we saw that more often than not that one would, as an example, would complete, 2 would complete, but somewhere in the middle, 3 or 4 might have failed. And, well, that could have been multiple reasons, but we saw in our observability that we could just start breaking them out. We saw this natural order that we can start dividing things, and instead of having everything run as an entire process, we can have it run in these smaller functions themselves. So let me double click into what I just said. So when this giant restore process fails, the only way to complete this was to rerun this giant restore process. That's costly. You're basically redoing function 1 through 2 or wherever it stopped again. Milestone 3. Milestone 2. What we wanted to do was add a durable layer, and durable in this case meant step functions. Step functions? I'm sure there's some sort of shape here, right? Yeah. Okay, cool. We still had the queue there. The queue still enqueued the job per se, but for what this job ended up doing, let's delete this for 1 second. Our worker job took the initial job itself and was able to read in the step functions, the DAG, the graph on what order to process things, and it did a fan out to process all of these. So we no longer have a we no longer have a giant restore process, but multiple of these processes. So it would take these functions but it would re-enqueue into SQS. This is the fan out job. This is now the fan out job, let's call it. And let's do it that way. Okay. That looks okay. A little cluttered here. I'm trying to save space on my screen here. But let's zoom out and see what happened. Our front-end application for a site restore is now an asynchronous request with a durability layer, meaning that I'm going to enqueue this job for a general site restore as a whole, and that says to me that I'm going to fan out by reading the step functions DAG, the directed acyclic graph of dependencies of what this is and how to run a step function. And after this fan out, it basically re-enqueued, so fan out back into the queue. And then this fan out job, this process was really just the site restore job now, but to run all of the functions. So fan out job is really just running whatever function that was passed in. So if function 1 was passed in, it's going to run function 1. If function 2 is passed in, it's going to run function 2, etc. up until it completes. Yeah. That's more or less it. It was now in this case we're gonna modify our paint bucket here, but in the case where I have 3 functions here, but this is function n, in the case here where let's say function 2 fails for whatever reason why, like if the pods are restarting, this ends up having retry logic, and it'll only retry this specific function. Function 1 already completed as green, so say this right here completed. Did I click on the right? I clicked on the wrong thing. This right here rather completed. This failed. This did not even run. So function 1 is considered done. It won't try again. And this is all part of that one same job. Function 2 failed, so it'll only retry function 2. That's it. It's a pretty more or less a simple system. Wasn't too difficult. The things that I'm like, if you're double clicking on, like how do you handle observability, we added custom metrics pretty much everywhere. So all these individual functions, I think I mentioned this a little bit earlier, they are instrumented with statsd metrics, where you wanted to have the stop times of each, or if it was just completed, success, or failure, and those would just alert properly with AWS step functions metrics. For a distributed lock, since we have Kubernetes here, so multiple pods are able to just trigger jobs, we are actually using MongoDB as a distributed lock here. It worked really well. There's like a small collection here to signify that it was a snapshot job, and all it did was saying it was started, pending, failed, or completed. So those 4 states. That's it. Cool. Yeah. Glad I got that off my chest here. At least in a diagram in a dialogue way. All right. Cool. Thanks.